What is up, everyone? Welcome back to the shop. Most of the time, I'm a very happy-go-lucky guy, but the past few days, I've been completely frustrated and stressed with this issue. It's driving me crazy. But I think we're getting closer to finding the solution. Angelo and I have been working together really closely to help figure this out. So, we have this issue where the pivot head is not sitting flush. It just won't go flat, and they should be like completely level, flat, flush, but they won't. So there's obviously some sort of mismatch between the way the two things are made. So when we make a handle, we make all the backside dimensions first, which is great. You have your critical tolerances there, and the pivot and the stop pins and the diameter and the threads, and everything critical is in the first op. Even the lock bar cutout. This is all done from the backside, which is awesome. And then you go to flip them over onto a fixture like this. They're located by two pins right there and there, and here and here. They have ever so slight bit of wiggle. I think we measured 6/10. There has to be slop in the system for everything to work, and that's okay. But there's tolerance stack, and this is the kind of things I'm learning, you know, having Angelo on board and running into problems and situations where tolerances add up from one part to the next, from one locating pin to the next, to the next, to the next. I gotta sneeze. Woo! Like Eric was asking me, why didn't we have this problem before? Before we were running just one fixture, same fixture every time, all the time. It never changes. That's great. Now we're running two fixtures, my old fixture and one of the new fixtures from Amish. Things are ever so slightly different. Maybe mine is weird, maybe his is weird, probably mostly mine. His is probably more two-spec and mine's probably a little weird. So we're battling this like ever so slight difference between the two, and trying to make the perfect part every time, and we're having a lot of rejects coming back from Eric going, the pivot doesn't fit. So then we have to put it back on the machine, we have to recut it, we have to offset it a thou or half a thou or something like that. And then Angelo and I were looking at all the dimensions and looking at the pivot, measuring a batch of pivots. We have our tolerance there. So the tolerance here, plus the tolerance range of that, plus the tolerance range of the locating pins, plus the tolerance range, oh man, of the locating pins here onto the main pallet. All of this adds up and adds up and adds up and adds up, and it reduces the amount of actual slop you're allowed to have. So it's one of those things where it's like the more you learn about it, the deeper you dive, and the more difficult it becomes, because it just gets harder and harder and harder. However, I think we have some good ideas. Take it away, Angelo.
Great ideas.
So I gave the intro. I talked about tolerances are hard.
Yep. Tolerance stack.
Yeah, so there's this term that's been thrown around, GDNT, geometric dimensioning and tolerancing, right? Explain that.
Well, you're defining features in order to essentially control a product. So if I was to say, I want you to make this part 5.5 inches by 7 inches, I didn't tell you to make it square. I didn't tell you that these two sides have to be parallel. I didn't tell you that, you know, there has to be symmetry, or in any of your holes there has to be any positional tolerance. So we use basic dimensioning, which is sometimes you'll see, we'll show you, I guess in a picture, a basic dimension on a drawing. You use those basic dimensions essentially to determine your GD&T for positional tolerances. Our issue here is we have a tolerance stack issue from one fixture to the other to our pins.
Yeah.
So there's layers of it that add up.
And so say you got one thou here, and then another thou here, and then another thou here. Yeah. That's like 3/10 of actual, or whatever it is.
Yeah, it adds up. And
no, but the variance gets tighter and tighter and tighter.
Yes, exactly.
You're allowable.
Yeah, big time. And there's only so much you can achieve. So there's no such thing as hitting, you know, perfect zero on anything.
Yeah. Like we can hit a 10th on a part.
Yep.
But a part plus another part plus another part plus another part.
And also measuring it. That's where it becomes a big concern. So we're able to make these, but where it gets more difficult for us is we don't have a CMM or fancy equipment like bigger shops do in order to validate it all. So we have to essentially check it with a little bit more conventional methods with the indicators and the probe. However, we have some solutions to it. We've kind of figured out where the error is.
Yep.
Using indicating the actual.
Yeah. So we're putting these parts on the mill. We're taking the probe. We're measuring that hole, or we're trying to measure these pins, or we're taking a dial test indicator and we're sweeping around one of the pins. So
and that told us that we were ever so slightly off on one of the fixtures to the other.
Yeah, so these two center pallets are slightly different.
And we're talking thinner than human hair.
Yeah.
But it adds up. And when you want to achieve a perfect gap, and with the tolerances we have, did you mention how tight those?
I mentioned some of them. Yeah. No, I didn't actually. So our pivot going into the bottom, going into the hole there. We have two machine dimensions. The hole gets machined from this side, and then it has to be accurately flipped over, and then this has to be machined to there. And we basically have to figure out what is the positional error allowable between the hole and the head for the thing to fit. Now, of course, we want a very tight fit because we don't want this big ugly gap. And if there is a big ugly gap, we want it at least even around the outside. So we want it really, really, really freaking tight.
Yeah.
And
it's 6/10 and 9/10.
Yeah. So it's I looked in the CAD. According to CAD, perfect scenario. It's 6/10 on each wall and 9/10 top and bottom, which is weird that it's off, but whatever. So that's 6/10 on each side that we can't screw up. And as we're multiplying pallets and getting bigger, and
there's variance in our pivot where we have to have a variance there. So we keep it pretty tight. I think it's under 1 thou as well. But again, you have the stack up, so it can get smaller again from
here.
there.
You mean?
The actual head. So the head.
Oh yeah, the width of the head. Yeah.
Yeah. So we keep that to 1 thou. So there has to be some range there to be realistic in order to make things. So it ends up being a tight fit. And our true position for that bore is, and the bore and the counter
bore. Yeah, the head pocket
would be. Is really tight. So our fixturing needs to be very good. We've had one fixture able to make it all the time because we've adjusted for that. Now we have two running the same program, so we have to essentially
compensate for one and not the other.
Yeah. There are some ways to do it moving forward. We will end up pressing in larger pins and milling them in situation.
I like that idea. So where we press in these two pins and they locate the part like that, Angelo came up with a suggestion. You press in a bigger pin, you mount this on the fixture, on the vise, on the table, in a perfect real world scenario, and then you take your end mill and you come around and you make that the size you want.
Yep.
And we can do one round, one diamond, which is the proper way to do it.
And then we can check it with an indicator on the machine to validate what we've done.
So that should be true position, or whatever you call it.
Yeah.
So you make one round and that becomes your rotating, and then the diamond just stops it from going this way. It doesn't need to stop it from going that way, right?
It still controls 12 planes of movement once we have it screwed down, so it's a proper way to do it.
All right. But the quick and dirty way that we're going to do it, we're going to install a new probe tip. So this is the tip we're using right now. That's the one we're going to be installing. Large difference, as you can see. You've got a ceramic shaft here versus a carbide shaft here. My only concern is that it's got to reach everywhere it needs to reach. When it's probing stuff, I don't want a problem, but I don't think it'll be a problem. We are switching from the big ruby tip, I think it's a 6mm tip, to a 2mm tip, I think. 2 or 3? 2. I have a couple areas that I'm not sure if it'll work, so I'm looking right now, going, it currently touches the side of the blade, so I need to make sure there's enough clearance that it'll actually touch the side but not rub on the shank up top. I think that'll work. There's a couple of other areas where it touches. It touches here on the angled blades fixture. I think that's going to require a tweak because of the angle and the ball size and all that, which I'll look into, but I think switching from that to that, we only have to offset the length of the tool, set it again, dial it in for concentricity, and then tell the machine the ball diameter, which should be in one of the variables. Probably I'll look right now. Yeah, it's that one, it's 500. I think that is the ball diameter. But I'll look in the Renishaw catalog or instruction manual to see what that exactly is. My theory is I want to probe inside that hole so that we have the true position of that bore that's machined on the other side. So you mount it over here, you go in, and you'll be able to probe that hole, and then you can finish machine. Just like, these are the only two critical features. These have a bit more slop, these have a bit more slop. The clip mounting has a bit more slop. Everything else is not nearly as critical as this guy. So if we go in and we probe every handle, we know it's going to be bang on.
Yep.
In so much as the accuracy of the probe and the run out of the probe, and we'll verify all of that.
And everything.
Yeah.
Which should bring us to where we need to be.
It should bring, yeah. And then in the future, as we make more center pallets, we'll make them better. And we learn from our experiences and we grow and we get better. So I'm relatively happy, like thrilled with this solution. A little bit of programming, I'm not too worried about it.
It adds
like a minute of cycle time, yeah. I think we're already using the probe for something else, so it'll just come in.
Yeah, we're probing the faces to determine the average height.
Right.
And because it's about what? We allow about a thou.
A thou max.
A thou max.
Most of them are less than half a thou variance in thickness, but that affects how deep the pivot sits in the handle. So assuming this would go all the way down, a thou thicker or thinner handle might make the pivot stick up or down by a thou. Now, for those of you guys who have no idea what a thou is, piece of paper, regular paper. Let's check this out.
4.5.
4 thou, 3.5, 4 thou.
Yeah, there you go.
So we are trying to achieve a tolerance 10 times less than this, if not more. Okay, so we got 4 thou for a paper. All right, measuring a human hair, 2 thou hair. I guess I have thin hair.
So that's about how far off that was.
So in our measuring, one of these pallets is this far off from the other one, which is nothing. Like in real world, I lost it already. 2 thou is nothing. But in manufacturing and machining, 2 thou is a lot. It's a mile sometimes. Yeah. So this is the kind of levels we go to for the knives that we make. It has to be this way for us to be happy, and I just want to be happy. So I got this at the Tormac Open House 2016, and don't really have a use for it, but we're trying to think of like some microphone interviewing situation. Dude, look at that.
There you go.
Hello. Hello.
Yes.
Hello, yes.
Oh, very good.
What are your thoughts about this?
This is much better than putting it up my shirt every time.
There you go. Should I make it so that's hidden? It just looks like you're talking to a...
Trying to shove a wrench in your face.
Yeah, I like it.
This is what happens when 2 OCD engineers try to make a microphone with very little effort. All right, so we're machining some other stuff that we have to machine right now, and then I'll be able to replace the probe tip. But we use this paper-based chart to track what we did basically every day. We've got a section for the mill and a section for the lathe. The lathe has been so busy lately, it's been fantastic. 3 months, it's been running every single day, almost all day, sometimes till like 12 or 1 o'clock at night, unattended. Amazing, like we're killing it on the lathe. And on the mill too, except for problems like this. So it really bugs me when the past few days, rework, repair pallets, bevel catch-up, rework, fixing, catching. It's just like, oh my gosh. I don't want this to be my life. So we have to fix the problem, which we're doing, and then move forward. And then you go back like a month to where we were just running the one pallet, and it's like production. Everything's really good. So mistakes are fine, problems are fine, everything's great, but you have to be able to learn from them and hopefully not do them again. Otherwise, it's just not great. So there's always going to be problems, and I'm totally fine with that. You just got to learn from it. I found them. In here is one special tool that I'm looking for. this little gap down here. There's actually a picture in the manual that what this gap is for. So I want to share a pro tip with you guys. This little gap down here in my Moridura vertical, I always wondered kind of what it was for, and in the instruction manual it actually shows a picture of a guy going like this. And I'm like, oh, that's dumb, nobody's ever going to use that. I use that all the time. You know, I'm doing it here, and then I go to reach something over here, and then I love it. It's funny. Okay, so I found a special tool, removing the thing. On this machine, there's the workpiece measuring probe, and then the tool length measuring probe down there. We're going to change the length of that by installing the new tip. So they say you can't touch that to the tool setter because there's going to be error in one of them. Now, I think one of the springs is much softer than the other, so I think it'll be fine, but we're going to do some verification right now to figure that out. So how you're supposed to measure that is some sort of shim method, kind of, you know, use a piece of paper that's 1/4 thou or a shim that's 2 thou or something, and kind of jog it down until the paper doesn't move. I just want to see if this way works because it's way easier and like better if it works. All right, so Angelo's writing down the current tool length that we think it is. I don't know the last time I verified it, but we're going to check this tool for runout real quick before we take it apart. Runout is definitely one of my obsessions. The spindle in this machine is so good, you can just effortlessly spin the tool. All right, that runout is freaking amazing. Less than 1/10,000th of an inch. Now remember, we measured a piece of paper and a hair and it was like 2 thousandths. This is 1/10,000th of an inch. 10 times less than 1 thou. This is the circularity of the probe, and as you're measuring, you know, faces, this side, face, circularity matters, or maybe circularity is the wrong word, but concentricity, runout, matters incredibly. So, old setup was bang on perfect, I love it. We're gonna do this again for the new setup. So right now we're doing the touch together method. Okay, I think we're good. I can see the bottom one moving and doing the, I think the spring on the bottom one is softer than the spring in the plunger. All right, so we're running the same code again here. We just want to see the consistency of that number. Same. Bang on. Yeah, we'll do it again. Because there's a spring in the probe and there's a spring on the tool setter. You can see it moving now. If one spring is much harder than the other, then we're good. Ole. And we're back. So a couple days ago, it was a Friday and I was stressed and I was having those problems and I couldn't figure it out and it was driving me crazy. And then like late Friday, I noticed a couple things that really helped clear my head, except it was Friday and I couldn't fix it and I had plans on the weekend with the kids. So yesterday and now today is Tuesday, I was able to implement the changes. Everything is much better. Clearly, ever so slightly, old palette to Amish's new palettes, they're slightly different, and that's okay. There has to be tolerance range and everything. But the root of the problem is that I never calibrated my Renishaw probe. If you come in here and check this out. So here's the Renishaw OMP60. I previously had this tip on there, which won't fit into the pivot hole. So I put now the 2mm with a tungsten carbide shaft on it. I did that this morning. I came in at 5 a.m. and got that thing all set up, dialed in with zero runout. Maybe we'll show a scene of the runout right now. You want the probe to have no runout because then it just measures accurately. Although there's a calibration routine that kind of doesn't care about a little bit of runout. But the problem was I had dialed in my probe to have zero runout, except there was a substantial amount of compensation in the calibration values, so that basically the machine thought the probe was off center even though it was dead on center. So I was getting readings, you know, maybe up to 2 thou different than where it's supposed to be, and that is a problemo. One of those hidden things that I didn't even realize because I skipped a step along the way at some point. Probably the last time I broke that tip. I put it in, dialed it for 0, touched off the X, called it good, didn't calibrate it. And that was a mistake. So I just called Frank Cox Metrology today. They are shipping me a ring gauge, about, what do they say, 1 1/8 bore diameter with a class XX tolerance, which is pretty much the best you can get. So you want your measurement equipment to be much finer precision than your actual usage. So I don't want a gauge made to a 1/10, I want it made to a 1,000,000th or whatever is the next one down. So it should be really, really good. So that's coming in so I can properly calibrate the probe. However, I got this one installed and I did calibrate it on basically the most precise hole I could find, which is the hole that goes right in here. In our blades, we have that Cogsdale bearing tool that comes in and makes a beautiful hole. And with pin gauges, I was able to verify what size that exactly is, you know, within a 1/10. And I calibrated the probe, I put it in there, I calibrated a bunch of times. And then I did a bunch of checks, testing between various known dimensions, and it seems to be super duper 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 good. That was phase 1. Phase 2 is, the problem is, the center hole is done in the backside up, and then it gets flipped on the fixture pins like I told you about before, and then this has to be machined, and I want them to be like perfect. So I've got the smaller tip, it now comes in, I stayed up late and I created a custom probing code that goes into the hole, touches off, and resets the X0, Y0 at the top corner of the fixture. It was complicated, but super worth it. I don't know. So basically now it comes in, it touches off the hole position for that hole, and then machines that pocket based on that exact center line. For each individual handle, they should be absolutely perfect. We did our first test, and perfectly smooth and flat. We looked at it under the microscope. They are visually dead center, and very happy with that. Set up here, I've got the Noga base, which these things are awesome. You loosen them, adjust it to wherever you want. With a Mitutoyo 1/10 dial test indicator, I'm going to jog the machine until that teeny tiny ball is touching that teeny tiny ball. They're basically the same size, which makes this kind of annoying. There we go. All right, so get a close up on the dial there. So the point is not to get this to 0, although I will just for fun, because it'll work in anywhere basically. So now if I come in and I spin this, it's got, what is that? Can you read that dial? Like how close can you get on that? It's got 1/2 of run out. This morning it was nothing, it didn't even move. But I guess through a little bit of use, it moves. So the first thing it's gonna do, it's gonna come in and check to see, is there a handle there? If so, move over to center. Probe in X, probe in Y. I said those backwards. And then it's gonna move over to the second one. Check, is there a handle there? Probe in Y. Probe in X. And then it's just going to pause and wait at this point. So what it's doing is it's storing these values into some backup, into 185, 6, 7, 8. So that I can reach into them and call them later and as needed just for that pivot hole, so I don't mess up the rest of the fixture. So it's just like a temporary storage spot. And then in the 650 range, here is my XYZ for fixture 1, XYZ for fixture 2. This number is based on the top corner. So 27.661 versus 27.6612. So we're only 0.2 different, which is phenomenal cosmic power. Using my new microphone, man, we really care about measuring. It's just gotta be so good for us to make a good product. And it's not just that I care, it's that we've developed a product that requires it. You know, there's downsides to that, but there's also super upside, because when we nail it, it's fantastic. So it's very important for us to understand the problem and be able to fix it permanently, because as we scale this company and as we grow, I don't want this ever to be a problem ever again. So let's figure out the solution. You know, there's the temporary one that we're doing right now, and then there's the long-term solution of building better, more accurate fixtures. All of that together is going to really help us in the future. So hope that helps. Hope you learned something. Thanks for watching. Don't forget to like and subscribe, and I'll see you guys next time.